All right. Hello. Good morning, Alex, Victor, Prince, Neo, and Trisha. So, welcome to, I think this is week 11 of the semester. Good morning, Denmark, as well. Di ko alam kung nabati kita. Pero anyway, yeah, this is week 11. So, we are in the almost the home stretch of the semester. And again, in the past few days, siguro before I go to the actual technical discussion, just some housekeeping matters first. I uploaded some sort of a handout in the module for Math 191. It's the module on the L curve regularization, but this is the set of modules that I wrote for Math 175. Sorry, excuse me. So if you guys have taken Math 175 and the L curve is still new to you, so you're excused from the class today. Although I'll be showing, or I will be demonstrating a code applied to the ill post problems that we saw last time, or in the last or the first half of the semester. So yeah, you can stick around. You'll get something new at towards the end. Pero kung sawa na kayo sa L curve at tandaan niyo pa to from last semester, then you can excuse yourselves for today, or you can do something on the side and then just wait for us to look at the MATLAB code once again, all right? Because again, this is a rehash of the Math 175 modules that I have last semester. And I think tama ka ba, Frazel? Ikaw yung nag-encode nito. So thank you, Frazel, for encoding this during the summer. Which reminds me as well, I have a post in the Facebook group ng students of the math division. Dun sa mga juniors dyan, especially yung mga F-Math majors, uh, I shared a link to an internship opportunity from Citibank or the Citi Group. So if you're interested, kindly check the link. Sabi nung contact ko sa Citi, hindi required na F-Math or AS major ka. So as long as you have the qualifications, you have taken, or if you think you can do the job na naka-describe dun sa application page, then you're free to apply. And a piece of advice, if you will be taking the practicum on the coming mid-year 2023, so start looking for possible placements kasi yung ibang companies ang aga nung kanilang call for applications. So katulad nga nung City, last quarter ng year yung kanilang application period para dun sa internships that will start on June or in the summer of the next year. So simulan nyo na maganap kasi yan yung nagiging problema namin during the mid-year. Kasi usually mga student, nag-start pa lang sila maghanap ng pag-applyan, say, after the second semester. Yung pagitan ng second sem at saka mid-year, medyo mahirap. At saka yung mga companies, minsan mabagal sila mag-process ng applications at saka ng agreements with interns kasi last priority nila yung interns. Marami silang ginagawa sa kanilang companies. So start as early as now, hunting for internship opportunities. And then I guess the last, I still owe you the problem set. I'll try really to finish grading them within the week. All right. Kaya nga nagbabait ako sa inyo na hindi na ako magbibigay ng problem set 1.2, tapos yung problem set 2 ay i-reserve ko na towards the end of the semester. Siguro in 2 weeks time, ibibigay ko na yung problem set 2 para tapos papagaanin na natin yung lectures para makapag-focus kayo dun sa final project. Ano? Mabait ako sa inyo kasi ang dami ko pang utang sa inyo. So, anong utang ko sa inyo? Yung problem set 1. Tapos, I think, hindi ko pa nagagawa yung write-up nung heat diffusion. Although, I shared with you the notes or the excerpts of the book by Siltanen, which you can read because nung ko naman binasa yung discussion, I think I mentioned I'll either share with you the PDF annotations or the PDF notes that I wrote live on class, or I'll make a nice typewritten document. So I'll try to also do that. Pero if you need those concepts, you can revisit the videos na lang muna for now. Okay. And then lastly, I think hindi ko sure pero parang may nakita kong post last week about the availability of the student evaluation of teaching effectiveness in SAIS. So that's my request to you guys. Towards the end of the semester, don't forget to evaluate me. And actually, all of your instructors and professors via SAIS. Ano? So, isang nagiging problema namin ay napakakakaunti nung nagsasagot nung student evaluation of teachers. That's the official measure of how effective your teachers were. So kung gusto niyo gumante kasi pinahirapan kayo, so, hindi, joke lang yun. Kung gusto niyo gumante kasi hindi effective yung teacher niyo, or you want to give appreciation to your teachers for doing a good job, sagutan niyo yung teacher's evaluation. Kasi yun nga, yun yung pagkakataon niyo to have your voices heard. So kung hindi talaga kayo satisfied, parang ano lang yan, parang umorder lang kayo sa Lazada, ano? So, you give a good rating if you got good services throughout the semester, or give bad reviews if you didn't get good service, ano? Ang nagiging problema lang namin yung mga ano lang, yung mga galit na galit yung yung nagsasagot. So, isa or dalawang students, they will give a failing grade. Pero, I mean, yung mga satisfied, medyo hindi sila nagsasagot. So, but whether you're satisfied or not, whatever your evaluation would be, you're highly encouraged to do this, because the more students who will respond, the more accurate that assessment is. Kasi yun yung ginagamit namin para sa mga official functions like promotion, application of grants, renewal of those in temporary appointments, ano. So yun yung nagiging basihan. So we want to get to hear from students. And pangat. Yeah, I think that's it. So towards the end, saka don't worry kasi hindi naman makikita ng teachers nyo kung sino yung nag-comment o sino yung mga nag-grade sa kanila. And that's usually released to us siguro at least, hindi pala at least, usually months after the end of the SEM na yung nabibigay sa amin. Alright? Actually, since bumalik ako nung June 2021, wala pa akong nababasa na student evaluation. Hindi pa nila sa akin binibigay. So there's no way for us to get back to you. So give your honest assessment in that evaluation through size. Okay? All right. So as I've mentioned earlier, good morning for those who just came in. I hope you can see my screen. Let me know if you can't. I was telling kanina that today we'll be talking about L-curve regularization. So if you were my students in Math 175 last semester, this would be very familiar. In fact, the module that I uploaded in our Canvas website is the modules from last semester, so you can do something else for the good part of this session. But towards the end of the session, I'll share with you, or I'll demonstrate the MATLAB code that I also uploaded in Canvas kani-kanina lang, which will allow us to implement the L-curve process with the inverse problems that we were solving. Because remember, our problem with the inverse problems, or the strategies that we develop to solve inverse problems, ay napaka-susceptible or sensitive nila with respect to noise. Remember the convolution process? Dun sa convolution process, kapag perfect data yung nasa right-hand side natin, say, kinuha natin yung matrix A that models how the convolution acts on a certain function f. Tapos, diniscretize natin yung function f into a bunch of points contained in the vector little x. Yung A times x, siya yung magbibigay sa atin ng image after the convolution. All right? This is a discrete approximation to the convolution, and say this is equal to b. Right? Now, of course, if A is square and it is invertible, we learned how to solve this system, right? So ito lang ay x equals A inverse B, which is good, all right? Because you get an exact solution because A is invertible. But the problem is this solution might be susceptible to noise. And true enough, this is what we have seen in the first few weeks of our classes, wherein we did a naive reconstruction of the function f. It worked well with perfect data. Kaya lang, at the moment that we include some measurement noise in our system, naging ax plus b plus epsilon na, kasi actually this is what happens in the field or in the actual application. Pag meron kang isang physical phenomenon, magsasolve ka ng inverse problem, you want to find the source or the input x that will give us the data measurements b ng na nakuha natin from the field, so hindi natin nakukuha yung perfect data because our data might be tainted by noise, maybe through channels or by the way it was collected or the way it was transmitted. So in one way or the other, there could be some noise in the measurements. Or in the sense of a physical measurement, yung epsilon, ito ay isang maliit na measurement noise because there's no perfect measuring device. So instead of AX equals B, ang sinusolve talaga natin or ang nasusolve talaga sa mga physical settings ay AX equals B, which is the true data, plus measurement noise or data noise, epsilon. And then you will do naive reconstruction. Halimbawa, kinuha mo yung naive reconstruction. Say this is x prime. Sinolve mo yung A inverse times B plus epsilon. Tapos, pag kinumpare mo to dun sa true solution, sabihin natin yung true solution ay x tilde. Since this is an inverse problem, and inverse problems are ill-posed by nature, your x tilde, or sorry, your x star, this x star, might be very far from x prime. Excuse me. Yeah. And that is due to the very nature of inverse problems. Ibig sabihin, for most inverse problems, so for most inverse problems, yung x tilde or yung x star, which is the solution, the true solution from perfect data is far off from the solution from noisy data. So this might be a big number. The relative error or the relative difference between the true solution and the solution from the noisy data might be a large number, right? And this is what we call sensitivity with respect to noise, all right? Kasi yung maliit na epsilon usually is around 1% or less of the 1% or less of the size of the right-hand side. So, pag kinuha nyo yung L2 norm ng epsilon, or epsilon plane gamit ko, no? L2 norm yan, divided by L2 norm ni B, this is say around 1%. And that 1% error might give us a very huge relative difference between the true solution and the solution from the noisy data. Okay, and as mathematicians, we don't want to leave our solutions like that. All right, or kahit ano ka, kahit applied scientist ka, physicist ka, biologist ka, engineer ka, ayaw mo na napaka-susceptible nung iyong solution sa measurement noise or sa measurement error. Kasi halimbawa, ang kailangan mo para ma-secure yung foundation nung binubuo mong building ay X star. Okay? Pero nung nag-measure ka, ang nakuha mong solution ay X prime. Now, if X star is very far from X prime, you might not get the target that you wish for. Baka hindi mo makuha yung gusto mo talagang totoong foundation para dun sa building mo. So that measurement error might kill the entire process. Okay? So, ano yung solution? Well, a primitive solution is to find a more accurate measurement device. All right? So kung sensitive siya sa 1% noise or sa 1% measurement error, bumili ka ng mahal na equipment that will give you more accurate measurements, say to the order of 10 to the minus 5 or 10 to the minus 6. And you have your fingers crossed that you will take away the sensitivity from the problem, right? Pero halimbawa, nag-start, unang-una, budget concerns, all right? Can you afford such a very expensive measurement device? Number two, available ba yung mas accurate na measurement device? Kasi usually measurement devices ay hanggang, say, 0.5% to 1% lang talaga yung accuracy. I talked to some physicists when I was in the US. We're trying to build an experiment. Tapos sabi nila, imposible mong makuha yung 10 to the negative 10 na gusto mong accuracy because meron kaming sinosolve na problem. Tapos it's a defect detection algorithm in a one-dimensional spring. Ano? So, kailangan namin 10 to the minus 10 yung accuracy kasi nung in-implement namin yung numerical solution, ang laki ng error. Kailangan yung error wag lumampas ng 10 to the minus 10. I mean, in terms of the data, para hindi mag-propagate yung error. Sabi ng mga physicists namin, oy, imposible yan. Walang measurement device ng accuracy ay 10 to the minus 10. So we need to scrap the solution scheme that we developed for 6 months. 6 months naming tinabaho yung problem. 6 months kaming nag-isip ng solution scheme only to get a very sensitive solution scheme at the end of the 6 months. Tapos ang aming saving grace sana merong measurement device na kaya yung 10 to the minus 10. Kaya lang wala. So naging physically or I mean practically irrelevant yung ginawa naming research. So we have to look for another way to solve the problem. All right? So and then so yun yung dalawang cons ng pagganap ng measurement device na mas accurate. And here is where us theoretical or applied mathematicians will factor in. Mag-iimbento tayo ng method on how to minimize the effect of the noise in the solution. Tapos nakita natin to when we talk about, say, the convolution process. Remember? Nung nag-convolution process tayo, ang ganda nung solution kapag ka perfect, ang ganda nung reconstruction kapag ka perfect data yung ginamit natin. Pero once na ginamit natin yung data which is tainted by measurement noise, ang pangit na nung reconstruction or ang layo na nung reconstruction from the actual function that we are trying to get. So ang tanong ngayon, paano natin matatanggal yung epekto nung noise na yon mula dun sa pagkuha natin ng solution. And one way to do this, or actually the easiest way to do this, is via the L-curve technique. And I hope you will appreciate the power this gives us. Kasi nga kung walang mga numerical scientists, numerical analysts, or mathematicians, ang magiging posibleng remedyo lamang ay humanap ng mas accurate na measurement device. Pero tayo mga mathematician, kaya't nating umimbento ng paraan kung paano masicircumvent yung problem of sensitivity with respect to noise. And that's what we'll be talking about right now. And this is the L-curve or the L-curve technique. Okay. Let me just scroll down. The first half of this module talks about the Moore-Penrose pseudo-inverse, which I think I already introduced to you in one of the meetings because I was reviewing my notes kahapon kung magsisimula ba ako dun sa section A nitong module na to. But I saw one video in our playlist na nag-discuss na pala ako ng Moore-Penrose pseudo-inverse sa inyo. So that's one way to solve a system kapag ka hindi invertible yung matrix A. So matrix A might be square and yet its inverse doesn't exist, or A is not square, so magkakaroon ka ng problema, so kailangan talagang pseudo-inverse yung gamitin mo. So if you already forgot that, or you're interested in a more in-depth treatment of the Moore-Penrose pseudo-inverse, so you can revisit section A. Kasi super basic lang yung ginawa kong introduction dun sa pseudo-inverse in section A. Right? But our focus dun sa earlier weeks nitong semestre, our focus will be on the L-curve. All right? So tingnan natin, how is the L-curve implemented? Now, our discussion will be more on the implementation side. Yung theory niya ay I think is masyadong malalim for an undergraduate course. It's a whole bunch of theory. It's regularization theory. This would be heavy on optimization, heavy on functional analysis. Kaya hindi ko talaga dinidiscuss yung meat ng theory behind the regularization techniques and why they work. All right? So ang focus lang natin on the undergraduate level ay kung paano siya i-implement. And let's just be happy for now na, okay, nag-work siya. The question, bakit siya nag-work, may be revisited in more advanced courses. Okay? So let's see how this is done. So again, we consider a linear system, ax equals b. So that's what we want to do. But in practical scenarios, as I mentioned kanina, hindi b yung nakukuha natin na right-hand side, but b plus epsilon, where epsilon is your data noise or measurement error. Okay. And usually, the size of epsilon is small compared to the size of the right-hand side vector in terms of the norm that you're using. By default, we're using the L2 norm. So usually, ang gusto nating size ni epsilon or ang relative size ni epsilon with respect to the data is about 1%. Okay. So kapag ka ganyan yung relation, ibig sabihin 1% yung noise. Dapat ma-minimize natin yung epekto ng 1% na noise na yon doon sa ating solution. Right? In fact, if x tilde is your solution from the noisy data and x star is the solution from the actual or from the true data, we want them to be as close to each other as possible. So we want x tilde minus x star to be much, much less than 1. Okay? Gusto natin, same order. Halimbawa, 1% yung noise. So siguro tatanggapin natin if the relative difference between the two. So that's x tilde minus x star over x star. Tapos L2 norm yan. Siguro tatanggapin natin between 10% and 1%. Okay? Kasi 1% yung ating epsilon. So within the same order of magnitude. So it's order 10 to the 0%. So hanggang 10% siguro matatanggap natin. But anything beyond 10% might be too much. Okay? Now, so the thing here is, saan nanggagaling yung problem with the sensitivity with respect to the right-hand side vector? Well, in theory, this sensitivity can be quantified by using the condition number K of the matrix A. Pwede mong tingnan kung magkakaroon tayo ng idea kung gaano ka-sensitive yung ating inverse problem with respect to measurement error or noise in the data by computing the condition number. Ang condition number ng isang matrix ay yung norm ng matrix times the norm ng kanyang pseudo-inverse. So A plus is the pseudo-inverse of A. In most cases, the pseudo-inverse is also the normals, which is also the inverse of the normal matrix. All right. So if you forgot about it, yung pinakasimpleng pagko-compute ng pseudo-inverse, but this will only work for a good class of matrices. Ano? Pag nag-solve ka ng AX equals to B, tapos si A ay hindi invertible, or mahirap computein yung kanyang inverse, what you do is to multiply both sides by the conjugate transpose of A. Pag sinabi natin conjugate transpose, kukunin mo yung transpose ni matrix A, ibig sabihin yung row number at saka column number, pagbabaliktarin mo, tapos kung complex numbers yung laman ni matrix A, kukunin mo yung conjugate nila. Pero kung yung matrix A mo naman ay puro real numbers lang yung laman, so ita-transpose mo lang siya. Remember, A transpose is just yung matrix A pa rin, mga laman ni matrix A, pero yung row number at saka column number pinagbabaliktad natin. Right? Now, if your matrix A also contains some complex numbers or non-real numbers, ang kukunin natin ay yung A star, which is the conjugate transpose. The conjugate transpose is obtained by taking the transpose. Kunin mo yung transpose ng matrix A, pero kunin mo yung conjugate ng bawat entry. Right? Ang conjugate ng isang complex number, if you forgot, kung meron kang complex number A plus BI, ang conjugate niya ay A plus BI bar, and this is equal to A minus BI. Pinapalitan mo lang yung middle sign noong imaginary part, yung sign ng imaginary part. Okay? Kung positive real number times I, magkakaroon ka ng negative the real number times I. Yun lamang yung kanyang conjugate. Okay? And if your matrix A is M by N, yung A transpose at saka yung A conjugate transpose ay parehas N by M. This is not hard to imagine because pinagpapalit mo lang naman yung row number at saka column number. Yung first row siya yung nagiging first column, right? And then yung third column siya yung magiging third row. So nababaliktad lang yung role ng rows at saka columns pag kinuha mo yung transpose ng isang matrix. Similar yung mangyayari kapag conjugate transpose, ita-transpose mo muna siya saka mo kukunin yung conjugate. All right. Is that quick review okay? Kasi I know yung iba sa inyo baka hindi pa nagme-matrix algebra. So I hope that rings bells or nare-review kayo. Kung hindi familiar yung mga terms, sabihan nyo lang ako para I can discuss it in more details. Remember sa 191, chill lang tayo. Wala tayong hinahabol na course outline. So because I think I can finish the discussions in 1 or 2 weeks. Kung nagmamadali talaga ako, pero pwedeng hindi tayo magmadali. Okay? So yon, so kunin mo si A transpose o kaya si A conjugate transpose. So kung si matrix A ay hindi invertible, hindi siya square or mahirap or hindi talaga siya invertible pero square siya or mahirap lang kunin yung inverse niya, pwede natin kunin yung normal equation. And the normal equation is found by multiplying both sides of your equation by the conjugate transpose in general. Right? It's easy to see that if your matrix A consists only of real entries, A conjugate transpose is equal to A transpose. Okay? So, kaya ang gagamitin ko na lang para mas generic yung discussion natin ay, ay A transpose. Sorry, A conjugate transpose. So, i-multiply ko lang both sides ng A conjugate transpose, right? Which is valid, right? Because the matrix A, if we assume this to be M by N, ibig sabihin si A conjugate transpose ay N by M. So in the end, the multiplication is well defined and A conjugate transpose times A will be N by N, right? Tapos most of the times, A conjugate transpose times A is invertible, okay? Ito pala, careful kayo dito sa matrix multiplication kasi hindi commutative ang matrix multiplication. So ang ginawa ko dito sa left-hand side, minultiply ko si AX, the original left-hand side, by A conjugate transpose to the left. So nag-pre-multiply ako ng A conjugate transpose dun sa left side. So mag-left multiply din ako or magpe-pre-multiply ako ng A conjugate transpose dun sa right-hand side. Nung equation natin. Hindi pwedeng isulat nyo na AB star because in the first place, AB star might not be well defined, right? Because what is the size of B? If this is M by N, matrix X will be N by 1. So that means the matrix B is M by 1. All right? Pero remember, si A conjugate transpose ay N by M. So the multiplication is well defined. It will result to an N by 1 matrix, which is fine. Okay? So be careful dun sa ordering. Now, again, as I've remarked earlier, most of the times, A conjugate transpose times A is invertible, and usually it's easier to find its inverse than the inverse of the matrix A if the inverse of matrix A exists, all right? So your solution, let's call this X, let's call it X star, is A conjugate transpose times A inverse times A conjugate times B. And this is what we call the normal solution. Kasi nanggaling siya sa pagsosolve ng normal equation instead na isolve diretso yung matrix A, yung matrix system natin. Right? And if you remember from our discussion of the pseudo inverse, this guy could be called A pseudo inverse B, right? Where A pseudo inverse or A plus is the pseudo inverse of A, and in most cases, it is computed by A transpose A inverse times A transpose. Or when I say transpose, conjugate transpose siya. Right? So ito yung tinatawag natin na Moore-Penrose pseudo-inverse. Okay? And this is a generic way of computing the pseudo-inverse if this guy is invertible, which happens most of the times. All right? Kapag ka ito ay hindi invertible, hindi nyo mako-compute yung pseudo-inverse this way, you need to find another way. Kasi ang kagandahan sa pseudo-inverse, it's the generalization of the matrix inverse. In the sense na lahat ng matrix, kahit ano yung itsura ng matrix na yon, kahit rectangular pa siya, kahit ano yung itsura ng mga laman niya, lahat ng matrices ay may pseudo-inverse. Hindi katulad ng talagang inverse. Hindi lahat ng matrices ay may inverse. Pero lahat ay may pseudo-inverse. Okay? And one way to compute the pseudo-inverse is this way. Okay? Pagka hindi to kayang computein, and the only problem that you might encounter is the non-invertibility of this matrix, merong alternative ways. Nandun sa section A yung alternative ways kung paano mako-compute yung Moore-Penrose pseudo-inverse. And usually the Moore-Penrose pseudo-inverse, as I've mentioned, is much computationally cheaper than computing the inverses of a matrix A. And ang kagandahan din, isa pang kagandahan ng pseudo-inverse ay kung invertible ang matrix mo, ang pseudo-inverse niya ay yung inverse. So it really generalizes inverses. Ang ginawa nyo lang, dinefine nyo lang ano yung magiging pseudo-inverse ng isang non-invertible matrix. Kasi kung invertible na yung matrix, siya na rin yung inverse niya na yung pseudo-inverse. So this has a very consistent theory behind it. So kaya maganda siyang gamitin. But, and then most programming languages, kahit invertible yung matrix A, pag pinag-solve mo sila ng linear system, ang kinocompute nila ay pseudo-inverse. Alright? Kasi nga, mas efficient computein yung pseudo-inverse at mas stable siya numerically. In fact, kay MATLAB, madali siyang i-implement. Alright? So remember kapag ka meron kang AX equals B na matrix na define mo na siya kay MATLAB, gusto mo i-compute kasi si X, pwede mong gawin X equals inv of A times B. Yan yung syntax mo kay MATLAB para makuha si X. That's fine, although computing the inverse of A might be expensive and numerically unstable. Kaya it is not very recommended to use this in solving linear systems. At saka ang problema nga, baka hindi pa nag-exist yung inverse ni A. At kahit sure ka na nag-exist siya, baka magka-problema ka pa rin pag ito yung ginamit mo na line dun sa code. Alright? So alternatively, what you can do is X equals P in of A times B. Right? What P-inv does, it computes the pseudo-inverse of the matrix A. So si MATLAB na yung magko-compute para sa inyo ng Moore-Penrose pseudo-inverse. So pwede nyo itong gamitin or i-program nyo to. Okay? So ganito nyo kinocompute si P-inv. Kinocompute niya yung conjugate transpose ni A. Ang syntax dyan ay A prime times A. Tapos i-invert yan ni MATLAB. Tapos ita-times mo uli ng A prime. So yan yung mahabang syntax para sa pseudo-inverse. Pero built-in na kay MATLAB yung pagko-compute ng pseudo-inverse, eto na siya. Alright? Pero as a mathematician, it's nice to know na itong P-inv na to, ganito lamang yung ginawa ni MATLAB to find that. Right? May isa pang shortcut kay MATLAB, ito ay X equals A backslash B. So itong tatlo na to are very much related to each other. Okay. The only difference is that this will only work for a selected class of matrices, yung mga invertible matrices. Pero itong dalawa na to, they are the same, exactly the same, and they will work for any matrix A. And you will get the least square solution. All right? Yun yung kagandahan ng normal equation. Pag normal equation yung sinolve mo, you are guaranteed to get the best solution in terms of the L2 norm. Okay? Kasi minsan walang solution yung system mo, pero makukuha mo yung vector x that will give you the minimum residual with respect to the L2 norm. Okay? So yun yung titingnan natin. Now, How will this factor in? So paano na, so ito yung solution scheme, ito yung naive reconstruction. So these are approaches on how you can naively reconstruct the solution to the inverse problem, right? With or without noise. Pero nakita natin pag may noise na hindi na to ganon ka-accurate, right? Because the x that we can compute with b replaced by noisy data will be very far off from the intended result of our calculation. Yung x nating mako-compute using any of these three solutions when b is a noisy data ay posibleng masyadong malayo doon sa ating actual solution. Now, titingnan natin paano natin siya mako-combat, right? So, pero paano tayo magkaka-idea kung sensitive ba yung ating inverse problem? Well, at the back of our minds, we know that inverse problems are ill-posed by nature, ano? Pero to get uh, a more quantitative idea of how big or how sensitive our solution will be to measurement noise, titingnan natin yung condition number. Sorry, medyo pabalik-balik ako, no? So, ito yung problema pag nagla-live discussion ako. So, ano yung condition number? Well, again, as I've mentioned kanina, ang condition number ay ito. So, kaya ko pala diniscuss yung pseudo-inverse kasi kailangan kong computein yung norm niya. So, computein mo yung norm ni A, tapos computein mo yung norm ni pseudo-inverse, you will get the condition number K of A. Now, the bigger K of A is, the more sensitive the solution is to perturbations in the right-hand side. So gusto sana natin yung condition number sana ay mababa. Kasi pag malaki yan, malaki rin yung magiging relative difference between the solution from true data and the solution from noisy data. In fact, they would be proportional to the size of the noise, pero yung constant of proportionality ay yung condition number, as you see in this equation. So remember, we want this to be very, very small, right? Because this represents gaano kalayo, ilang percent yung layo ng noisy solution doon sa true solution. So we want this to be as small as possible. Pero sabi ng remark na to, this is bounded above by the condition number times the size of the noise. So if K of A, or the condition number, is below 10, so if your K of A is between 0 and 10, then you might be good. Kasi kung ito ay 1% times less than 10, so you'll have something less than 10%. So the relative difference will be less than 10%, then you might be good for some applications. All right? Ibig sabihin, yung 1% mo na measurement error ay nagbigay lamang ng up to 10% na relative difference between the true and the noisy solution. That could be fine for some applications, ano? Pero the condition number can blow up. It could be hundreds, it could be thousands. Yun yung magiging problema natin, right? So let's look at a quick example. Example 9.4 in this handouts, ano? So I have the rectangular matrix A here. I'm not sure if this is the one that pinagawa ko sa inyong homework, ano? Na meron tayong pa-Google form para dun sa noise na ilalagay nyo. But, or something similar to this, ano? So, this is the matrix A, and this is the matrix B. Gusto kong isolve yung AX equals B. And the true solution is 1, 1. So, because if you multiply your matrix A by 1, 1, so we get as first entry, 0.15 plus 0.1. Sorry, yeah, that's 0.25. And then 0.16 times 1 plus 0.1 times 1, we get 0.26. And then 2.02 times 1 plus 1.3 times 1, 3.32. So indeed, 1, 1 is the true solution for this problem. All right? Now, kapag sure ka na itong matrix B natin ay perfect data, and this is what you got from the measurement, meaning your measurement process is perfect or your data collection is perfect. So you will, a solution using the pseudo inverse will give you 1, 1. All right? So pag pinagawa mo yan kay MATLAB, ginawa mong x equals a backslash b, ibibigay niya sa'yo ay x equals 1, 1. The exact solution. Okay? And that is fine if you have perfect data. But if you compute for the condition number, And the nice thing about MATLAB, meron siyang shortcut pagko-compute ng condition number. Type mo lang yung cond of A, ibibigay niya yung L2 condition number ng matrix A. Meaning MATLAB will compute the L2 norm ni matrix A times the L2 norm of the pseudo inverse. Yun yung ibibigay niyang condition number. So yung condition number niya ay in the L2 sense, which is fine. Now, pag kinompute natin yung L2 ay yung condition number ni matrix A, makukuha natin ay 629.5801. Okay? So, ibig sabihin, kapag ka meron akong 1% noise dun sa aking data, alright, posibleng yung relative difference between the true solution and the solution from the noisy data ay maging around 630 times 1%. So that's 630% na posibleng error. Napakalaki ng posibleng error. So nakita nyo, yung 1% na noise, pwedeng gawin yan 629% yung layo ng true solution mula dun sa noisy solution. Okay? So to illustrate that the effect of the noise here, mag-introduce ako ng noise vector. Halimbawa, ang noise vector ko ay ito. 0.01, 0.032 at saka 0.01. Okay? So that means, halimbawa, kung nasa field ako, imbes na 0.25, ang nakuha kong measurement ay 0.26. Instead na 0.26, ang nakuha kong second measurement ay 0.292. Alright? At instead na 3.32, yung third data ko nakuha ay 3.33. Kasi nga, ito yung measurement error. Okay? Now, how big is that noise? Well, this noise is just about 1.05% of the true data. So, ibig sabihin, yung measurement error ko is around 1% lamang. Maliit lang yung measurement error ko. Ibig sabihin, ang ganda ng data collection process ko o ang ganda ng aking measurement device. Kasi napaka-accurate niya. 1.05% lang yung error. But remember, the condition number of our matrix A is 629.58. So, ibig sabihin, in the worst case, yung relative difference between the true solution when 1, and whatever solution I get from B plus epsilon would be around 1% times 630. So, it's around 630%. So, I should brace myself na napakalaki ng posibleng maging error dito. True enough, if you calculate it using MATLAB, so kunin mo si x equals a backslash b plus epsilon, right? Ang bibigay niya sa yung solution ay itong x tilde na to. And using our naked eyes, remember x star, the actual solution is 1, 1. Super layo nung nakuha kong solution, negative 3, 7.22. Napakalayo dun sa 1, 1 na ine-expect natin. Right? Now, we have a good fit kasi yung pag kinuha ko, gaano ka-accurate itong x tilde with respect to the noisy data? Well, napaka-accurate nung solution, less than 1%. Pagka tinignan ko, gaano ka-accurate yung aking inversion procedure? Kasi nga, gumamit ako ng pseudo-inverse, so baka naman pangit yung fit in the first place. So tinignan ko yung ax tilde minus b plus epsilon, meaning how good was the solution to equation 9.10. Gaano kaganda yung fit dun sa noisy data? Well, the fit is accurate up to 0.5%. So ibig sabihin na ma-match nung ating solution x tilde yung noisy data ay yung data na kinolect mo. Pero alam na natin na sa inverse problems o sa inversion in general, hindi ka dapat mag-rely dito because you will be committing inverse crime. Ano yung inverse crime? Kinompute mo yung accuracy ng iyong reconstruction base dun sa data na ginamit mo to solve the problem itself. Well, we use the noisy data, so hindi dapat dun sa noisy data mo solely ibabase yung accuracy ng iyong solution. Kasi otherwise, pag tinigilan mo na to, sinabi mo na, maganda na yung solution ko. Ang ibibigay ko na dun sa aking manager na solution ay negative 3, 7.22. Well, you would have committed inverse crime. Kasi nga kahit ang ganda ng solution nito, inversion is a very sensitive numerical process. So ibig sabihin, posible kang nag-commit ng inverse crime. Na-fit mo lang yung data mo na noisy, pero beyond that, hindi maganda yung nakuha mong solution. And true enough, if you compare the noisy solution that we got from the true solution that we obtained, kinuha mo yung L2 norm ng true solution minus the noisy solution divided by the L2 norm of the true solution, nakuha mo ay 5.23. Ibig sabihin, 523% yung layo ng solution from the noisy data from the solution of from the true solution. At ang laking problema nito. Halimbawa, ang example ko nga dito, if I remember it right, halimbawa meron kang automated surgery robot. Alright? Tapos kung halimbawa maggagawa ka ng incision dun sa katawan ng patient. Tapos gumawa ka ng imaging process para ma-identify saan ko dapat simulan yung incision dun sa aking patient kasi nandun yung tumor. So, kung sa totoong data, totoong measurement, dapat dun ka sa 11, 0.11 dun sa halimbawa sa tiyan niya, dun ka mag-i-incision. Alright? Pero dahil medyo may flaw yung measurement device na ginamit to collect the data to pinpoint where the tumor is, instead na sa 11 yung ituro niya na position ng tumor, alright? Kahit 1% noise lang or may measurement error lamang dun sa instrument, ang tinuro niya ay negative 3,7. So, ang layo nung incision at hindi mo makikita yung tumor. Okay? So, yun yung problema kasi 523% yung relative error. And this is in the ballpark of what we predicted. Using the condition number, we predicted 660% yung maximum o yung worst case na epekto nung noise dun sa ating solution. Pero yung totoong nangyari ay 523%. Okay? This estimate or this upper bound is very crucial. Dun sa mga nag-174 na alam niyo yan, ito yung error bound na tinitingnan natin. In the worst case, ano yung pinakamalaking posibleng maging error. And it gives us a good idea because we cannot compute the actual relative error because most of the times we don't have access to the true solution. Kaya nag-rely tayo dun sa worst case scenario. Ano yung pinakamalaking posibleng error? Yun yung pinagbabasihan natin. Ang sinabi nung estimate natin kanina, ito yung pinakamalaking posibleng relative difference between the true and the noisy solution. So ang alam natin, in the worst case, we will get 660%. Medyo swerte pa tayo kasi yung relative difference actual ay 523% lamang. But that is not good. Kasi napakalayo ng ating noisy solution mula dun sa true solution. Okay? Question. Now, how do we combat this? Sabi ko kanina, edi bumili ka ng mas accurate na measurement device. Kasi halimbawa, yung measurement device mo ay 0.001% na lamang yung error, ano? So, ito yung relative size ng epsilon over the true data. So, ibig sabihin, this guy, 0.001 times condition number, yun yung magiging relative error. So, ibig sabihin, pagka 0.1% na lang yung error, so na-divide by 10 yung ating noise or yung magnitude ng noise. So, ibig sabihin, instead of around 660%, around 66% na lamang yung magiging sensitivity o yung magiging relative difference between the true and the actual solution. If you can cut this even lower, about 0.01% na lamang yung noise, ibig sabihin itong condition number times the size of the noise will be about 6.6% na lamang. So that's 660 divided by 100. But that is still huge with respect to the size of the epsilon. That might work for your application. Sa practical scenario, okay na siya. Pero if you think about it, 2 orders pa rin yung nawawala kasi kung 0.01% yung possible error, almost times 6 yung nangyayaring epekto dun sa relative difference. So this might not be the best solution at all, even if you can lower down the measurement error or the data noise due to collection or data preparation. Okay? Now, paano natin siya i-combat? Ang pinakamadaling paraan ay yung L-curve. And the L-curve is a cheap way of implementing a Tikhonov regularization routine. Okay? So, dun sa normal solution, paggamit ng pseudo-inverse, sinusolve natin yung AX equals B using this. Ito yung optimization problem niya. We want to find X tilde that will minimize the L2 norm of the residual. Ito yung tinatawag natin na, ito yung tinatawag natin na residual. Or ito yung error. Kasi nga, ang kinocompute natin, ang gusto natin i-compute ay AX equals B. So we want AX to be very close to B. Or in other words, we want AX minus B to be close to the zero vector. Okay? And the zero vector will have L2 norm equal to 0. So essentially, the least square solution or the pseudo-inverse solution X equals A conjugate, A pseudo-inverse B, ito yung least square solution. Siya si X. Kung ito si X star, siya yung nagbibigay ng pinakamaliit na L2 residual. That is guaranteed. Alright? Pag kinuha mo yung normal solution, more Penrose pseudo-inverse times B, mami-minimize mo yung residual. And this is good if you have perfect data. But if you expect or if you suspect or if you know for certain that your data is tainted by noise or measurement error, ayaw mo lamang na i-minimize yung AX minus B or yung L2 norm ng AX minus B. Para makakuha ka ng isang solution na hindi sensitive sa measurement error or sa noise, instead of just minimizing the residual, minimize the residual plus the norm of the solution. Ito yung tinatawag na Tikhonov regularization routine. Right? Gusto mo maliit pa rin yung residual kasi gusto mo accurate. Gusto pa rin natin na yung AX minus B ay malapit kay 0. We want AX to match B. Of course, that's the entire essence of what you're doing. We want to get accurate solutions or accurate reconstructions. Pero at the same time, gusto nating ma-minimize yung effect ng noise. To do that, kailangan paliitin din natin itong alpha times the L2 norm of the solution. Okay? So, hindi lang natin pinapaliit yung residual, pinapaliit ko rin yung norm ng solution. Okay? So the idea here is we are striking a good balance. We are balancing accuracy with sensitivity with respect to noise. Kasi itong term na to dun sa objective function natin, ito yung nagbibigay ng accurate solutions. Mas maliit yung L2 norm ng AX minus B quantity squared, mas accurate yung solution. Pero kung yun lang yung titingnan mo, accurate nga siya, pero sensitive naman siya sa noise. Now, we might get super accurate results. Pwedeng napakaliit nung makuha natin ng L2 norm ng residual. So the idea is, can I give up some of that accuracy to combat noise? Kaya ko bang magsakripisyo ng kaunting accuracy para mapaliit naman yung sensitivity dun sa noise? So ito naman yung nagte-take care ng sensitivity sa noise. Okay? So that's the equivalent exchange here. Kasi there's no free lunch. Dapat mag-give up tayo ng something to get something in return. So in this particular case, we are giving up some of the accuracy in favor of getting loose of the sensitivity to data. Right? Now, ito yung komplikadong pagko-compute ng Tikhonov solution, all right, which is also called the minimum norm solution, all right? Kasi hahanapin natin si vector x na makakapag-minimize nito. Kaya lang ang problema rito ay mahirap to na optimization problem. It's a nonlinear optimization problem. So dun sa mga OR dyan, I guess you have learned how to compute or how to solve nonlinear optimization problems. Pero if you are good at solving optimization or nonlinear optimization problems, that's not enough because we also need to find a parameter alpha. Ano si parameter alpha? It's a regularization parameter that is a small number between 0 and 1. Okay? Kasama siya dun sa mga degrees of freedom doon sa ating optimization routine. Aside from finding x, kailangan hanapin din natin si alpha. Alpha is a number between 0 and 1 which will represents the weight or the bias assigned to the minimization of the L2 norm of the solution. Okay? Now, si alpha, dapat piliin natin siya in a very nice way because the optimal alpha will strike the perfect balance between the accuracy and the sensitivity with respect to noise. Kapag ka masyadong malaki si alpha, mafo-force yung ating algorithm to make the L2 norm of the solution very, very small. Because remember, the idea here is minimization siya, no? Gusto kong i-minimize itong sum na yan. So kung yung parameter alpha ay pipiliin ko to be very large, so malaki yan, mabibigyan ng mas malaking weight yung pag-minimize ng L2 norm ng solution. Let's call this the solution norm para mas maiksi yung binabanggit ko. So ito yung solution norm, norm ni X, tapos ito tawagin nating residual norm. Well, self-explanatory, norm ng residual. Ano? So kapag ka masyadong malaki si alpha, mafo-force yung optimization routine na i-minimize or i-prioritize yung pag-minimize sa L2 norm ni X. So ibig sabihin, liliit yung solution norm. Pag lumiit yung solution norm, nagiging less sensitive na yung ating solution doon sa noise. So, napakaliit na nung solution norm. So, makukuha mong solution, pag napakalaki ni alpha, makukuha mong solution ay napaka-stable niya with respect to noisy data. So, hindi siya naapektuhan na ng noise. Pero mapababayaan mo yung accuracy. Kasi dito magfo-focus yung ating optimization routine. So, mapababayaan niya etong accuracy. So, pag masyadong malaki si alpha, magiging stable yung solution pero hindi siya ganun ka-accurate. And conversely, if your alpha is very small, pag masyadong maliit yung alpha, so ibig sabihin, to begin with, this term is already very small. Kasi super liit na ni alpha, so kahit medyo malaki yung norm ni X na makukuha mo, liliit itong term na to. Kasi ang liit na ni alpha, mamumultiply siya by some constant. So napakaliit na ng second term, magfo-focus yung optimization routine mo na i-minimize ito. Okay? So ibig sabihin, napaka-accurate na makukuha mong solution. Kasi dito nag-focus yung iyong optimization routine. Pero maliit na si alpha, so ibig sabihin si X posibleng malaki. Kasi kahit malaki si X ay yung norm ni X, maliit naman yung multiplier niya na alpha, so this term will go down. So that means we have a very accurate solution, but it will remain sensitive to measurement noise. Okay? And you will see that this two goes hand in hand, all right? In the sense that this is just a special case, alpha is equal to 0. Ibig sabihin lang nito, wala tayong paki sa sensitivity. All right? Pero dito, fina-factor natin yung sensitivity, and an ultimate question there is, how do we select alpha? We know alpha should not be too large, alpha should not be too slow, alpha is a small number between 0 and 1, but how can we find alpha? Well, you can design a very complicated nonlinear optimization problem. Just put it there and then use some optimization methods or use some shortcuts. Ang ginagamit ko sa research ko, which I'm still thinking if I will share it with you kasi medyo technical na to. Gumagamit kami ng Morozov discrepancy principle para i-compute yung alpha. Tapos gumagamit kami doon ng Newton-Raphson na dinidiscuss sa Math 175 para ma-compute yung alpha and ultimately we'll get the minimizer X sub alpha. But that's a very tedious and a mathematically involved process. Okay? Now may mas simpleng paraan at ito yung preferred ng mga engineers. Alright? Ito yung ginagamit nilang pang-solve ng alpha. So makukuha pa rin nila yung Tikhonov solution or the minimum norm solution, which is the minimizer of this guy. Pero medyo ad hoc yung pagko-compute nila kay alpha. In a sense na isosolve nila yung linear system for a very dense set of alphas. So ibig sabihin niya pipili siya ng mga candidates para kay alpha. So they will divide the interval 0 to 1, okay, into say a million points. So kukuha siya ng 1,000,000 candidate alpha. Tapos sa bawat isang candidate alpha na yon, titingnan nila eto. Titingnan nila ano yung sum ng ax minus b squared plus alpha times the L2 norm of x squared. Tapos titingnan nila sino yung best sa kanila. So essentially, ang gagawin nila, kukumputin nila yung solution para sa, say, 1,000,000 alphas, tapos pipili sila sa 1,000,000 na solution na yon, sino yung pinakamaganda. But that is quite expensive. Alright? Kasi ang mangyayari, instead na mag-solve ka lang ng isang linear system, magsosolve ka ng 1,000,000 linear system. Makukuha ka ng 1,000,000 candidate alpha. Bawat isang candidate alpha, magbibigay sa'yo ng isang candidate x sub alpha. Tapos mula dun sa 1,000,000 kandidatong x sub alpha, dun ka pipili ng isang pinakamagandang solution. Alright? But the thing is, if you have a fast computer, that could be done. At yun yung meron ng mga engineers. Mas mayaman kasi sa atin yung mga engineers. So meron silang mga supercomputers that can do a bunch of calculations. Even if they have a very huge matrix, kaya nilang mag-L curve. Kasi magko-compute sila ng 1,000,000 o 10,000,000 alphas between 0 and 1. Kaya nila yung gawin, pipiliin nila yung isang pinakamagandang alpha. Alright? So parang trial and error. Ko-compute niya to sa lahat ng candidate na alpha, pipili siya ng isang best na alpha. Pero parang tayong mga mathematicians will frown on that. Number one, parang na-defeat yung purpose nung pagko-compute. Kasi nag-trial and error ka lang pinili mo yung pinakamagandang solution. And usually, at saka isa pa nating reklamo, hindi na kaya ng laptop natin kasi wala tayong mga supercomputers na equipment. Usually, ang meron lang tayo ay pen, paper, and our brilliant minds. Pero yon, optimization problem. Pero this works. Ito yung ginagamit ng mga engineers and also mathematicians also jump in the bandwagon. Meron tayong mga efficient ways na na-develop. Paano mababawasan yung itetest ng mga engineers. Tanda ko nga nun, meron akong sinosolve. Hindi na kaya nung laptop ko. So, sinolve ko siya dun sa office computer ko sa US. So, meron kaming computing server. So, parang meron kaming access. So, nag-connect ako dun sa computing server namin. Nagka-access ako sa 32 cores, 32 CPUs. Imagine, yung usual laptop natin ay quad-core, no? So, meron siyang 4 na individual CPUs. Gumamit na ako ng computing server sa math department. Meron na akong gamit na 32 cores. Tapos bawat isang core na yun, bawat isang CPU na yun, meron ng 32 gig o 64 gig na RAM. So sabi ko, kakayanin na to. Pero nung nag-run ako ng experiment, hindi pa L-curve yung ginamit ko. Meron pa akong Morozov na ginamit. So mas madali to supposedly. Inabot ng 1 linggo yung kinocompute ko. Imagine 32 cores, 64 gig of RAM, bawat core. And that is how much more equivalent siya sa ilang laptops. Kasi ang laptop ko ay quad-core lang, tapos 16 gig lang yung memory. Tapos, so, aabutin ako ng buwan kung sa computer ko iraran. Pero may friend ako sa engineering department. Sabi niya, meron kaming supercomputer na hindi lang 64 gig yung RAM. I think meron sila na terabyte yung RAM. Ano ba susunod sa gigabyte? Susunod na ba sa gigabyte ay terabyte? Terabyte na, no? So meron silang terabyte ang RAM. And they have more than 64 cores na kaya nilang ipahiram sa akin. So yung 1 linggo kong kinompute sa math department, probably 2 hours na run na nung friend ko sa kanilang servers. So ganun sila ka computationally capable. Yung hardware nila ay nandun. Okay? So kaya afford talaga nila na maggawa ng mga gantong kalaking computations. Alright? But again, end of story here, let's find the best alpha. Yun yung end goal. Whether you do an ad hoc or an exhaustive search, such an L curve, or you apply the modulus of discrepancy principle, which will entail a nonlinear optimization problem for alpha, and then you plug it in to get your solution X sub alpha. At the end of the day, kailangan lang natin ng alpha. Alright? So, ituturo ko ngayon yung L curve, yung modulus of discrepancy. I'll think about it kung kakayanin ko siyang i-discuss sa inyo without going through very tedious optimization discussion kasi alam ko ay ang iba sa inyo ay math na hindi nag-take ng mga fancy optimization courses, ano? So let me think about it over the weekend if I'll continue with that or will be just contented with the L curve technique like sa 174, right? Pero pag nahanap mo na si alpha, ito lang yung form ng solution. Okay? So pag nakuha mo na yung best alpha o yung optimal alpha, not too large, not too small, na-compute mo na si alpha, ito yung kukunin mong solution. Which is kamukhang kamuka nung least square solution. Kamukhang kamuka nung pseudo-inverse solution. Pagka ang alpha mo ay 0, makukuha mo, ito yung Moore Penrose, di ba? Ito yung ibibigay sa akin ni MATLAB pag nag-A/B ako. Alright? Pero you once you take care of noise, magkakaroon ka na ng non-zero alpha. I is the identity matrix of the right size. So tingnan natin anong size ng identity matrix dyan. So pagpalagay natin na si matrix A ay M by N. So ibig sabihin, yung A conjugate transpose niya ay N by M. So itong product na to ay N by N. So dapat si identity matrix ay N by N din. Right? Si identity matrix ay yung matrix na puro 1 yung laman sa diagonal tapos 0 na elsewhere. The property of the identity matrix, pag meron kang kahit anong matrix, nag-left multiply ka o nag-right multiply ka ng identity matrix, hindi nababago yung matrix. So parang siya yung unity ng matrices. Yung mga nag-111 dyan, siya yung unity, siya yung unit element, siya yung identity ng matrix multiplication. Ano? So pag, kumbaga sa arithmetic, siya yung times 1. Alright? So, tapos i-multiply mo siya ng alpha, so ibig sabihin, identity matrix lang siya na pinalitan mo ng alpha yung diagonal. And alpha is a very small number, and essentially what we're doing here is we are just perturbing the diagonal entries of A star A by a small number. So, kukomputin mo yung A star A, pero bago natin siya i-invert, alright? Kasi kung nagsusudo inverse ka lang, i-invert mo na kagad yung A star A. Sabi ni Tikhonov, pag nahanap mo na si alpha, mag-add ka lang ng alpha dun sa diagonal ni A star A. That's what we are doing here. Binabago natin ng kaunti yung diagonal ng A star A. And the beauty about it, pag binago mo pala ng konti, yung diagonal ni A star A, bago mo siya i-invert, essentially doing alpha identity plus A star A, makakuha tayo ng mas stable na solution. And the reason why that happens is not apparent here. Para ma-fully understand natin bakit ganun yung epekto nitong perturbation of the diagonal of A star A. Bakit ang laki ng epekto niya o ng consequence niya dun sa solution? Unfortunately, I cannot tell you why at this point. Kasi ang daming dadaan ng prerequisites bago natin maintindihan kung bakit itong napakaliit na change na to ay magbibigay sa atin ng mas stable na solution. But for now, believe me that that is true. All right? So, proof by ano na lang to? Proof by convenience. Kasi wala tayong time na i-discuss lahat. So, kailangan paniwalaan nyo ako na totoo yun. So, aside from proof by convenience, ano rin siya? Proof by authority. Maniwala kayo sa akin, totoo ito. All right? So, yun na lang yung proof ko for now. So, that's what will happen here. So, talagang hanapan lang siya ng alpha. Kasi pag nahanap nyo na si alpha, just carry on with this formula, you're gonna get a more stable solution. Isang solution na hindi na masyadong naapektuhan ng measurement noise. Okay? So tingnan natin sa isang example dito. Saka in particular kung paano natin i-implement yung L-curve technique, ano? So, dito binalikan ko yung system 9.10. Tingnan ko yung system 9.10 ulit. Ito yung system 9.10, ano? Yung sinolve natin kanina na ang actual solution ay 1,1, pero kapag nilagyan mo ng 1% noise yung right-hand side, ang makukuha nating solution ay negative 3,7, which is 523% off from the actual solution. So remember those numbers, all right? So 1,1 yung true solution. Kapag nagkaroon ka ng 1.05% na noise, negative 3,7.22 yung makukuha nating solution, which is about 523% away from the true solution. Ganon ka-sensitive yung matrix A o yung process natin sa equation 9.10 sa measurement noise. Pero tingnan ko, sige, gagamitan natin ng L-curve. Kunwari, so wala tayong high-tech na measurement device. So yun lang talaga yung afford natin na measurement device. Meron siyang 1.05% na error. Gusto kong pababain yung relative difference. 523% yung nakita natin kanina. So, paano natin siya masusolusyonan? L-curve technique. We use the Morozov solution. Okay? Or, sorry, the Tikhonov solution using the L-curve technique. So, paano natin siya gagawin? Sabi ko nga kanina, ang gagawin natin, utak engineer muna tayo, hahatiin ko yung 0 to 1 sa 1,000,001 points. Essentially, dapat 0 to 1. No? So, because remember, alpha is a small positive regularization constant. So, si alpha ay between 0 and 1. Pero sa computers, usual computers, kung IEEE double precision machine yung gamit mo, which is the usual case, machine epsilon natin ay 10 to the minus 16. Ibig sabihin lang nun, kapag meron kang number na times 10 to the negative 16 ang order, yun ay virtually zero na ang tingin ng computer doon. Kaya pag halimbawa nagko-compute kayo, ito yung usual na nakukuha kong tanong sa 174 ngayon. Medyo, di ba, meron akong module, paparecreate ko sa students yung solution para ma-check nila kung tama yung program na sinulat nila. Magpapanik sila kapag nakakita sila, kunwari, yung nasa module ay 3.2 times 10 to the minus 16. Tapos yung nakuha nilang solution, halimbawa ay 8.7 times 10 to the negative 16. Tatawag na sila sa akin, mag-chat na sila sa akin, Sir, tama naman lahat ng nakuha kong numbers, maliban dun sa isa. Ang number mo ay 3.2 times 10 to the minus 16, pero ang number ko nakuha ay 8.7 times 10 to the negative 16. My reply to them is always this. Machine epsilon na yan. Kasi usual machines 10 to the negative 16 yung kanyang precision. Ibig sabihin, any number smaller than 10 to the negative 16 might be considered zero. Halimbawa kay Excel, ang machine precision ni Excel ay 2 to the negative 52. Ibig sabihin, any number less than 2 to the negative 52 ay treated to be zero. And 2 to the negative 52 is about 2.20 something times 10 to the negative 16. Binary kasi si Excel, kaya 2 to the negative 52. But essentially, 10 to the minus 16, considered zero na yon. So kaya ang gagawin ko ngayon, pipili ako ngayon, ano kaya si alpha? Ang gagawin kong candidates para kay alpha ay simula kay 10 to the negative 16 kasi virtually zero na yon hanggang kay 1. Pipili ako dito ng 1,000,001 points. Okay? Pipili ako ng 1,000,000 equally spaced points between 10 to the minus 16 hanggang kay 1. Sila yung mga candidates ko para kay alpha. Okay? So sa bawat isang alpha na yon, meron akong 1,000,000 at isang alpha. Sa bawat isang alpha na yon, kukomputing ko yung x sub alpha. So ang dami ko ngayong candidate solutions. Meron ng 1,000,001 candidate solutions, one each for those alphas. Up sa bawat isang alpha na candidate ko. Tapos, paano ko malalaman sino sa kanila yung pinakamagandang alpha? And in turn, sino sa kanila yung pinakamagandang solution? Ang gagawin ko ay i-graph ko yung mga points na to. I-graph ko on a two-dimensional plane yung residual norm at saka yung solution norm. So, di ba meron na akong 1,000,000 at isang x sub alpha. Sa bawat alpha na yon, kukomputing ko yung residual norm at saka yung solution norm. Tapos ipa-plot ko ngayon sa isang XY axis o isang XY coordinate plane yung residual norm, solution norm. So sa x-axis, ipa-plot ko yung residual norm. Sa y-axis, ipa-plot ko yung kanyang corresponding solution norm. Okay? So in that sense, or in this example, I got this guy. And you will see why it is called the L curve. Kasi yung graph ng residual norm versus the solution norm, ang itsura niya ay pa-letter L. At sabi ng L curve principle, ang pipiliin mong best alpha or best solution ay yung solution na nandun sa corner ng letter L mo. Okay? So that is your regularized solution. That's your Tikhonov solution. Or that's the near optimal alpha. Hindi ko kasi sure kung ito talaga yung magbibigay kasi 'di ba medyo ad hoc to, pumili ng 1,000,000 at isang points. So meron na 1,000,001 candidates. Posibleng yung best ay wala doon sa aking candidates. Basta it could be very near to the candidate, all right? Pero out of the 1,000,001 alphas that we tested, yung nasa corner, yung pinaka-best. Redundant, pinaka na best pa. Pero yun yung best solution. So pipiliin kong alpha ay yung alpha na magbibigay sa akin ng corner. Okay? So bakit ganun? Sir, bakit yung corner yung pipiliin mo? Let's identify what happens here in this graph, right? Now, yung x-axis residual norm yan. Okay? So meaning the more you are to the left in the x-axis, the more accurate your solution is, right? Kasi residual norm yan. It measures the accuracy of your solution. So habang pumupunta ka sa kaliwa, paganda ng paganda yung iyong estimate. Alright? So ibig sabihin, kung accuracy lamang yung problema, yung ano mo, yung concern mo, well, pumili ka ng isang solution na nandun sa kaliwa. So kasi nga, ito yung papaliit ang error o ang residual, alright? So you will pick such a solution somewhere here if you're only concerned with the or somewhere here in the endpoint, the leftmost point. Yan yung pipiliin mo na alpha kung accuracy lamang yung concern mo. Kasi the more to the left you are, the more accurate your solution is. Pero if you are taking into account also sensitivity with respect to noise, you won't pick the leftmost portion. Why? Because yung leftmost portion, nasa pinakataas siya. Right? So, ano yung implication ng nasa pinakataas siya? Ang laki ng solution norm. Right? Kita mo, ito yung solution norm. Ibig sabihin, ang laki nung sensitivity niya with respect to the error. With respect to the noise. So, kaya ang gagawin natin, we want to be as close to the left as possible, but as low as possible. Gusto natin nasa kaliwa kasi pag nasa kaliwa tayo, mas accurate yung solution kasi mas maliit yung residual norm. Gusto natin nasa baba tayo kasi the more nasa baba ka, mas maliit yung solution norm. Maliit na solution norm, meaning maliit yung sensitivity niya sa noise. Kaya the best compromise is somewhere here in the corner of the L curve. Kasi rito, kapag pumunta ka pa sa kanan ng konti na lamang yung sensitivity na nalulus mo. Right? Kasi hindi na masyadong lumiliit yung solution norm paglampas dun sa point of inflection. Or dito sa corner na to. Sa corner na to, tingnan nyo, ang liit na nung nababago dun sa solution norm. Pero look at this, how steep the change in the solution norm is before the corner. Pero after nung corner, medyo mabagal na lumiliit yung solution norm. So hindi na worth it na pumunta ka pa sa kanan nung corner kasi pag pumunta ka pa sa kanan nung corner, hindi na ganun kalaki yung inililiit ng solution norm pero lumalaki yung residual norm. So kaya yung corner na yung pipiliin mo because that's where the most significant decrease in the solution norm occur. All right? So am I making sense here? I hope I do. All right. Now, sir, paano mo ma-harvest yung Paano mo ma-harvest yung alpha? Kasi nakatago rito si alpha. Kasi yung nasa graph natin, residual norm. So this is how big the error is. So y-axis yung solution norm. So kailangan nyo ngayong i-save yung alpha na nagbibigay sa'yo ng bawat point dyan. Nakatago si alpha in the back end of our code. Kasi posibleng ito yung x sub, ito yung nanggaling sa x sub 0.000001 halimbawa. So kailangan ma-retrieve natin sino yung alpha na nagbigay sa atin ng corner. Alright? Don't worry, in-automate ko to sa MATLAB. So dun sa shinare ko na code, pag-usapan natin sa Thursday how to do it. Pero there's a nice way kay MATLAB na i-graph ni MATLAB itong L-curve. Tapos ang gagawin ng user, i-click niya lang yung gusto niyang corner o yung gusto niyang point. Pag click ni user dun sa corner, compute ni alpha, ititrace ni MATLAB, sino nga ba yung alpha na nagbigay ng kinlik ni user. Alright? So it's a little amazing. And at least for me, na-amaze ako nung may ganun palang functionality si MATLAB. May graph, mag-click ka lang ng point, ibibigay ni MATLAB yung coordinate ng point na yon. Pag alam ko yung coordinate, kaya kong bumalik dun sa data na sinave ko, mariretrieve ko si alpha na nagbigay sa akin ng corner na yan. Okay? But we'll play with the code next time. But if you do that, ang ibibigay sa ating alpha ay ito. 7.81 times 10 to the negative 4. Etong alpha na to, yan yung near optimal alpha. I mean, of all the candidates, of all the 1,000,001 candidates that we have for alpha, siya yung nagbigay ng corner or pinakamalapit sa corner ng L-curve. So that's why siya yung pipiliin ko na near optimal alpha. So ipa-plugin ko tong alpha na to dito sa formulas 9.12, alpha times identity matrix times A conjugate transpose times A, i-invert ko, i-multiply ko sa A conjugate times B. Right? Makuha ko si X sub alpha, the best X sub alpha out of the 1,000,001 solutions or candidates that we have. Well, ano yung resulta? Ito yung nakuha ko na X sub alpha. Pag 7.81 times 10 to the minus 4, yung kinuha ko na alpha, ito yung makukuha ko. 1.09, 0.87. And you see, this is much closer to 1.1 than the solution na nakita natin kanina. Super layo ng solution na nakuha natin kanina, right? But this is a little bit closer to 1.1, the true solution. All right? Maganda yung fit niya dun sa noisy data. Pag tinignan mo gaano siya ka-fit dun sa noisy data, 1.03% yung fit niya sa noisy data. At makikita nyo, oo nga no, nag-sacrifice tayo ng konting accuracy. Kasi yung example natin kanina, if alpha is 0, I mean, if we don't care about the noise, ang nakuha natin kanina ay 0.0056 yung fit doon sa noisy data. So that's 0.56% accuracy with respect to the noisy data. But now, I sacrifice half of that, lumaki yung error dun sa fit dun sa noisy data, umakyat siya ng 1.03%, meaning I gave up something. I gave up something to gain some sensitivity. Nag-sacrifice ako ng konting accuracy para makakuha ng additional stability. Alright? And true enough, tingnan niyo yung relative difference between the true solution and the true solution from the noisy data. Kanina, ilan yon? 523%. Pero ngayon, 11% na lamang yung naging relative difference. And you see how great this is. Kanina, 552% yung relative difference, mamamatay yung pasyente mo kung medical yung application. Kasi instead na sa 1.1 mo siya lagyan ng incision, o sa 1.1 mo siya simulang, ano bang Tagalog dun sa incision? Basta dun mo siya gamitan ng scalpel sa 1.1. Dun sa noise, dun sa measurement device mo kanina, ang ibibigay sa'yo without L-curve ay sa negative 3.7 or baliktad. Basta it's 552% far away. Pero ngayon, same equipment, same 1.05% measurement noise, pero saan tayo ituturo ng solution mula sa L-curve sa 1.09, 0.87, which is just about 11% off. And that's a very big improvement. And you see the power this has. Hindi natin kailangan ng mas accurate na measurement device. Mag L-curve lang tayo, makukuha natin ay mas magandang solution with respect to uh, measurement noise. Okay. So I think I should stop here. Do you guys have some questions? While you're thinking about questions, just a sneak peek on what we'll do next time. Isip na kayo ng question if you have some. Tingnan nyo to. I hope you can see my screen. Sorry, ulitin ko. Okay. Now, kung matatandaan nyo, dun sa convolution, sana nandito pa kasi ang bagal mag-run ng MATLAB ko eh. Okay. Dun sa convolution problem natin, ang ganda ang ganda ng solution kapag perfect data yung ginamit natin. Pero once na gumamit tayo ng noisy data, right? So ito yung ginamit natin na data instead na actual data yung gagamitin natin. So kumuha tayo ng points mula dun sa ating graph ng convolution. Nagulo yung figure. But anyway, tapos nung nirun natin yung simulation, tapos naglagay tayo ng 1% noise. So ito yung mga noisy data na nakuha natin. Ito yung nakuha nating reconstruction versus the actual solution. Right? Makikita nyo, kaproblema yun pa rin yung problema ko. Yung graphics ko kay MATLAB 2022 BI, hindi ganun nagre-render ng maayos. Pero kung matatandaan nyo, ganito yung itsura nung nakuha natin using the noisy data. So ang laki ng difference niya from the true data, which is the one in green. Pag niran ko yung L-curve, ito yung makukuha ko. Ito yung makukuha kong reconstruction. Okay. Same noisy data yung ginamit ko, pero with the aid of the L-curve, so mas malapit na yung nakuha kong reconstruction than the naive reconstruction. Right? And this is how we take care of measurement noise. So on Thursday, we'll talk about the MATLAB code. I already shared it with you guys. So pag-usapan natin sa Thursday, paano siya i-implement. All right? Or i-demo ko kung paano siya i-implement. I-explain ko line by line ano yung ginagawa niya para magkaroon kayo ng idea paano siya i-modify at i-tailor fit para sa project na gagawin nyo. Kasi dun sa project na gagawin nyo, meron kayong problem, i-discretize nyo siya into a linear system, tapos gagamitan nyo ng regularization procedure. So, pero yung code para sa regularization procedure, using the L-curve, ibibigay ko sa inyo. Para hindi nyo na siya kailangang i-program, i-call nyo na lang siya kapag nagawa nyo na yung matrix A at saka yung noisy data nyo. Alright? So that's it for now. Any questions, guys? Okay, so yes, Victor.
Sir, medyo curious lang sa code. Matagal din ba yun mag-run yung code na yun, sir? Or mas mabilis kaysa problem set?
Good question. So, medyo matagal siya. Lalo na ngayon sa laptop ko kasi hindi nagkakasundo si MATLAB 22B at saka yung laptop ko. So siguro it took probably around 5 minutes to run 1 million simulations. Kasi nga 1 million yung candidates ko. Nung nirarun ko to kanina, siguro nasa mga 10 minutes yung run. Dati, I know, 3 minutes lang or 2 minutes lang, tapos ko na yung 1 million run eh. Ngayon, ang bagal ni 22B sa akin, kaya mga 10 minutes. Pero kung masyadong matagal pag nag-run kayo, tapos baka kung hindi kakayanin ng computers nyo, malaki si matrix A, or masyadong malaki yung 1 million alphas, pwedeng liitan nyo lang yung alphas, pwedeng 10,000 alphas lang. Alright, tapos gawin mo lang siyang between, say, 10 to the minus 10 to the minus 10 hanggang 10 to the minus 3. Tapos kumuha ka ng 10,000 candidates mula doon or 1,000 candidates doon. I-refine mo na lang siya later kung may makikita ka na mas magandang solution. So, pwedeng ganun. So, kung masyado siyang matagal, untian mo lang yung alphas. So, yun yung magiging ano natin, magiging remedyo natin. Alright? Yun.
Thank you,
Pero
sir.
yung pagko-compute, okay, yeah. Yung pagko-compute ng matrix A, that's another question. So, siguro, mag-land kayo ng some time para i-compute si matrix A. Kung masyadong malaki si matrix A at matagal siyang i-run, i-save nyo na si matrix A. Siguro ipapakita ko next time paano nagsisave ng data kay MATLAB para pwede nyo siyang computein ngayon pa lang, tapos i-save mo na lang siya para next time, pag magre-regularization na kayo, i-call nyo na lang yung data nyo na matrix A. Lalo na kung hindi naman nagbago yung matrix A nyo, pwedeng nakasave na siya sa isang file, i-call na lang siya ni MATLAB para hindi nyo uulitin yung computation ng matrix A. Sana pala nasabi ko yung dati, no? Para yung ginawa nyo sa problem set 1, na-save nyo na sana. Pero sige, pag-usapan natin yun on Thursday. That was a nice question. Thank you, Victor. Other questions? All right, so kung wala na, thank you guys for coming today. Let's see each other again on Thursday. Until then, keep safe, guys. Bye-bye.
Thank you po, sir.
Thank you, sir.
All right.
Thank you po, sir.
Okay.